Hello everyone. Our project is the Digital Companion for Obesity, sponsored by Novo Nordisk. We would like to start off by thanking our technical directors who have been immensely helpful in the development of this project and have given us great feedback and insight. We have a 5-person team consisting of Afolabi Abiyomi, Justin Watkins, Dela Olivo, myself, Connor Vincent, and Yashaswini Mandalam. Founded in Denmark in 1923, Novo Nordisk has a long-standing history in the medical industry as one of the first companies to produce insulin. They have been crucial in the research and development for the treatment of chronic illnesses such as obesity, diabetes, Alzheimer's, and sickle cell disease. They are currently well known for their extremely effective obesity drug, Ozempic. Today, obesity is a widespread disease, affecting millions worldwide, with the amount of people suffering from this illness increasing every day. There are few treatment tools available to help those with obesity, and it is a very difficult disease to deal with alone. Depression and social isolation are notoriously associated with obesity and unfortunately make the disease much more difficult to deal with. Those suffering from obesity can also deal with several comorbidities, simultaneous diseases that occur in a patient. Examples include diabetes, hypertension, and obstructive sleep apnea. Our goal with this project is to create a device that will act as an essential tool to assist those suffering from obesity. An iOS app will connect a user to digital resources and information that will help them on their journey to live a healthier life. A compact smartwatch design with an array of sensors will give crucial biometric data on a patient. This data will be used in machine learning algorithms to personalize a patient and effectively treat those with obesity. This device seeks to be as non-invasive and seamless as possible, but still able to make great changes to the health of a patient. Currently, the smartwatch industry is a huge market worth $33.5 billion. Wearable technology, including smartwatches, is valued at $420 billion. With 1 in 3 Americans utilizing wearable technology and a large portion of the U.S. population suffering from obesity, there is a huge market need for a device that is directly targeted towards this disease. Our team has accomplished the creation of 2 different machine learning models to measure the physical activity and stress of a patient. A data pipeline that will transmit this information has been set up to connect the iOS app to a cloud server. Front-end design of the iOS app has been created to interact with the user. Heart rate sensor exploration has begun, as it is a crucial aspect of understanding and collecting biometric data for an obesity patient. An adaptable testing hardware device is also being used to further expand our team's sensor capabilities. Currently, I have been working on the health smartwatch, the hardware aspect from our team's project block diagram. I have been tasked with evaluating and working with the various different sensors our team is planning to integrate. I have done printed circuit board design to work on our prototype revision 3 that is shown to the right. Schematic work was done with the team to include necessary components we wanted on our revision 3 board, and our PCB layout was focused on having a development platform that was easy to modify. Finally, I have also been working on the assembly and testing of these PCBs. Here we have the various parts of our revision 3 board that we found crucial to include. There will be a battery input to our board that will be handled by the power management schematic. Sensor inputs will allow varying different sensors to be connected to the board and will make the development very modular. A heart rate sensor will be soldered to the board as it is a crucial biometric that needs to be measured. Finally, on the left side of the board, we have the display, audio output, and buzzer that will be a way to communicate with the user. Currently, we have acknowledged the importance of temperature and electrodermal activity sensors to gain increased insight into a user's health, specifically to record data associated with stress. Now, we will move to our next designer, Yashaswini Mandalam.
I'm primarily working on the machine learning portion of the project. My tasks involve setting up prediction models to predict eating activity and stress. Since our goal is a digital companion for obesity, understanding the eating activity of our user will be a major point in helping them manage their health. Predicting stress can give us insight on the user's emotional state and can be an indication of sleep problems, decreased motivation, and possible stress eating episodes. Identification and mitigation of stress is therefore an important prediction to understand and improve the overall health of the user. I have also been working on documentation of the data used to train these models for future references and improvement. Machine learning has 3 major parts. First, we have the data which is coming in from sensors, like the accelerometer, gyroscope, and heart rate. Second, we have our machine learning models that are taking in sensor data as input. And third, we have the trained models generating output, which in our case is predictions of eating activity and stress. For the eating activity recognition, I trained and tested a model called long short-term memory, or LSTM. This is a type of recurrent neural network that is able to remember patterns in long sequences of data. It takes an input, extracts features from the data by doing some calculations in the hidden layer, and gives an output prediction based on what is learned during its training stage. The model is trained using accelerometer and gyroscope data as input. An accelerometer on a smartwatch gives a measure of how fast someone's hand is moving. The gyroscope is measuring the rate at which a person's wrist rotates based on X, Y, and Z coordinates. The model is trained on labeled data from these two sensors, collected while a user eats different food, like sandwich, chips, and pasta. The data for training was obtained from a study that had test subjects do different activities, including eating, while a smartwatch with these sensors collected data at a frequency of 20 Hz. Currently, this model is giving 70% accuracy during testing, since identifying eating activity with these sensors alone is difficult. Improving that accuracy is part of the future goals of the project. Next, we have our stress prediction model, which uses random forests to predict stress. The model was trained on stress data collected from a research study. During testing, multiple decision trees individually decide if the test data shows indication of stress based on learnings from its training on labeled stress data. These decision trees make the decision of stress or not stressed, and then the majority vote of all the decision trees becomes the final prediction of the model. The input to this model comes from three sensors: heart rate, skin temperature, and electrodermal activity, or EDA. The EDA sensor measures the changing electrical properties of the skin. These changes are caused by alterations in sweat secretion and therefore help in stress prediction. This data is passed to the model, which is tested and trained to predict stress. The accuracy of this model is currently in the 90s, and it's pretty promising for our project. This is an overview of the major machine learning milestones, and now we will move on to our next designer, Afolabi Abayomi.
I'll be going over the cloud computing aspect of the project, and for this we've chosen to use the Amazon AWS service. I was assigned the task with the goal to implement a robust cloud storage solution integrated with machine learning capabilities for efficient and scalable data management on the AWS cloud service. This will be tailored for integration into the Novo Nordisk platform for the AWS service, which we are to go by. Our approach involves utilizing AWS for not only its cloud storage, but also for its effective machine learning algorithm and effective cost management. By implementing cloud storage deployment on the Novo Nordisk platform and the AWS service, we aim to optimize data accessibility, reliability, and security. Furthermore, the incorporation of AWS allows us to effectively manage costs while ensuring a scalable and intelligent solution. In addition to that, we will also incorporate the machine learning functionalities directly into the cloud storage system, enabling advanced analytics, pattern recognition, and data-driven insights. The cloud platform not only streamlines the storage and retrieval processes, but also processes meaningful information from the stored data using machine learning algorithms of the SageMaker. The presentation highlights the strategic use of cloud storage, effective data pipeline, and the great use of the AWS service for a comprehensive and effective solution. This slide highlights the data pipeline from the user's smartphone app to the cloud storage service that we will be utilizing. It sends the data retrieved on the phone app to the cloud storage, which is to be stored in the S3 bucket, and then sends it to the AWS Amplify for some data specifications, and then to the Amazon SageMaker for data processing, which will then derive personalized messages to best fit the patient's current situation and help them and guide them to a healthier lifestyle. This is the cloud infrastructure diagram to show how the information will be sent to the cloud and then back to the patient's phone app. Up next will be our next designer, Dela Olivio.
So my efforts were in hardware and iOS application, which consisted of revising schematics, completing layout designs, and front-end design and implementation for the app. On the right side is an image of our second hardware revision, compacted into a 2x2 board capable of tracking the user's heart rate and displaying the data on the screen. Our goal for this revision was to make a compacted board that could give us an idea of what our smartwatch could look like in the future. As you can see in the image, the components were compacted in such a way that would leave the OLED screen on top of the board with the sensor just below it. Developing this design also gives us the opportunity to begin tracking user data and start training ML models as we continue to develop hardware improvements. This diagram shows us the flow of data from the watch to the phone. Here we start at the watch where the data is gathered from the sensors and then transmitted via Bluetooth to the app. The app then converts this data and displays it as charts, progress reports, and other graphical representations. This is useful because it allows the user to track their data and eating habits over time and adjust their behavior accordingly. In the future, we plan on implementing ML algorithms that expand the app further by providing the users a more personalized experience based on their data and needs. This will be done alongside our next designer, Justin.
My efforts were focused on the schematic designs of both Rev 2 and 3, which consisted of designing the power charging and battery capability and sensor ports. I also did embedded programming for Rev 2, back-end development for the app, and devised the overall machine learning framework. As of now, the first feature we have is taking the data from the heart rate sensor and being able to actually detect and average heart rates. But we also have the availability of detecting oxygen saturation levels directly from the same sensor also. The prototype board initially chosen doesn't have Wi-Fi capability, so we use Bluetooth to send the data to the app in order to continue processing, displaying, and sending this data to the cloud as the first portion of the data pipeline. Bluetooth had to be coded to work on both the watch and the app, and after refining the code over time, the data is now sampled at 20 times a second to match the training data inputs of the eating activity recognition model. Plus, the same IMU data can also be utilized to detect user gestures directly on the board, so we can prompt users with displays and still receive feedback even without a touchscreen interface. The back end of the application currently relies on the model view model architecture. This is the best way to be able to ensure there's no dependencies between classes and objects, which can impede testing and cause functionality issues. This allows us to have a robust data binding between the models which represent the data and business logic with the views seen by the user. The application backend mostly revolves around switching views and interacting via Bluetooth with the prototype. My final contribution to the project is really what merges our current efforts into our future goals. We have defined our ABOs, but the real question is, how do we achieve the project's motivation with the platforms we were designated to build? This is where we can combine the simplicity and the implementations we've explored with a new approach in integration with large language models. This comes to the idea of the large life contextual description model. Our current goals rely on being able to have a wide selection of sensor data, which can be processed by machine learning models. The results of the models and the sensor data itself can be used to create a static framework of intervention and display results which every other wearable device has the capability to incorporate. But the real idea is, how do we drive personalization, which can lead to actually getting across to people? How do we make the experience with our application one that actually helps people change their lives, especially in the setting of mental health and the significant mental hurdles that come with trying to manage obesity? Our goal is to tokenize both the sensor data results and the machine learning model inferences to allow a large language model to take these pieces of data to get a better contextual description of what is going on currently with the user. If you're suffering from stress, overeating, getting yelled at, all these contextual clues about you can be deciphered with the right mix of sensors and combination of deployed machine learning models. Tokenization is just a fancy term for being able to break down sentences into corresponding pieces of data defined as tokens, which are the actual input for a large language model to generate responses with. What we seek to do is represent the results from the sensor data in machine learning models to become the equivalent of what maybe a therapist or a doctor or a friend would describe as going on with you at a particular moment of time or over a period of time, and give that information in a usable format to a large language model. This allows us to be able to interact with already existing large language models to derive even more in-depth chat features by placing these contextual descriptions alongside user responses. Similar applications in language models have been made to have therapy sessions, give health advice, or simply act as a supportive friend. However, we can give these models a deeper insight right away and let them have more context about it. Plus, the intent of the project isn't just another chat application, but we plan to utilize this model to create personal messages that can intervene based on the data our platform receives about the user and their environment. With recommendation models, we can have the platform select certain interventions based on cognitive behavioral therapy, clinical science, and doctor and dietitian recommendations. With information from these sensors and machine learning inputs describing your current mental and physical states, we can produce a command token to give direction for how the large language model should structure its response and generate personal messages to send, notify, or speak to a user to attempt to keep them on track. It's the same concept as if you were too lazy to do a report on an article, so you go to ChatGPT, paste the article in, and type summarize this. In our project, the article is what our platform can discern about, while the summarize portion is equivalent to the command token that would tell the model, send them a supportive message about their progress. Overall, this model defines the rest of our future goals, and we're going to be focusing on getting more data from more sensors, more models built to process the data, and then creating the tokenization mechanisms themselves.